righty, hang on just a second. Okay, so I want to give you a little thumbnail sketch of the work that we're doing under a Dolly Award for seismometer to advance lunar interior structure knowledge. You can see over here on the left our objectives, basically to use seismology to understand lunar structure, taking advantage of passive and active signals that are generated, seismic signals that are generated. You can see down here at the bottom our team, which includes Renee Weber as our science PI from Marshall Space Flight Center, Danny Della Justina from the U of A, Brad Avinson from Silicon Audio, our partner providing the seismometer, Chris Zachney from Honeybee providing a burial system, which I'll outline here in a minute, Nick Schmurr from University of Maryland, Matt Siegler from PSI, and Veronica Bray from the U of A. So this graph gives you a pretty good idea of the events that we anticipate from the Apollo seismic data that we would be able to exploit, the signals that we would be able to exploit. So you're looking at frequencies on the x-axis, and you can see that the deep teleseismic signals are all below about 1 hertz, and the higher frequency signals run up to a few hundred hertz. The current performance of the COTS device is shown here with this thin blue line, and this device was developed for the terrestrial nuclear test ban treaty. It's been deployed as a COTS units around the world in quantities of several thousand. So its performance has been well demonstrated, but it hasn't been adapted to spaceflight. And it also hasn't been adapted to the requirements for the moon. And so what we're seeking to do is to make those two big steps with this seismometer. And the black curve shows the anticipated performance at the end of our development, improving the sensitivity and changing the detected frequency band. For reference, I'm showing the InSight VBB, which has a higher sensitivity, but over a more limited range. And also this green curve shows the noise floor as determined by the Apollo seismic data. Just worth mentioning, I think most people know that other than the Earth, the moon is the most studied seismic planetary object that we have. And up in the upper right-hand corner, you can see a single-axis COTS seismometer. So these things are quite small, compact. They don't use very much power. So here's our schedule. We're working our way through year one. We got this award last year. The money arrived at the U of A in the middle of the summer. So we're still, at about the 6 to 8 month mark. We are a little bit ahead of schedule, actually, in terms, and I'll give you an impression of where we are. The objective for the seismometer is to go from TRL4 to TRL6, and for the burial system to go from to TRL5. So let me give you a sense of the nature of the two elements of our experiment. The first is the Silicon Audio seismometer. It's a traditional electromagnetic force-limited sensor, meaning that it has a central permanent magnet surrounded by a coil, and then the motion of the coil induced by seismic signals is detected, the current is detected, and a feedback loop limits the motion, uses that signal and limits the motion of the coil. But and that produces an instrument that is essentially a geophone. The Silicon Audio innovation is to add a laser interferometric system that operates at about 880 nanometers, to further improve the detection sensitivity, similar to the way the LIGO instruments work, to picometer level displacements. So that's really the trick. A couple of advantages of this device. It is tilt insensitive. We do plan to provide a 3-axis device, but unlike some seismometers, it has a very wide range up to, in the terrestrial application, up to 90 degrees of insensitivity to tilt with respect to gravity. And it also operates equally well at 1 atmosphere and a hard vacuum. So unlike the InSight seismometer, which requires a hard vacuum both in fabrication and test on the Earth and also in operation at Mars, this device, covering a somewhat different frequency band and at a lower sensitivity, or a higher sensitivity, I should say, does not require a hard vacuum. The other component of our experiment is the Honeybee Robotics burial system. And this is notionally shown in these cartoons where you have a lander concept and the burial system is mounted on one of the legs. It's essentially a coiled tube that, when deployed, turns into a cylinder with the geometric rigidity of a cylinder, and then a gas jet system serves as the equivalent of an operating bit, so to speak. In other words, gas is flowed through the tube, out through vent holes, and that excavates the powdered lunar regolith out of the holes. And Honeybee has demonstrated this in one test to be able to achieve about a 1 meter depth in lunar simulant in a very short period of time with a very modest amount of gas. You can see the accommodation requirements over here in the lower right-hand side. We have a current best estimate of the seismometer system based on the engineering work that we've done. This includes the control electronics of about 4.2 kg. And we have a goal for the burial system of 5 kg. Honeybee is working their way in that direction. We're not there yet, but I'm optimistic that we're going to get there. Power requirements are quite modest, as you can see. One interesting feature about a seismometer experiment by comparison with imagers is that they operate continuously, especially since we're not taking our own active source to the moon. We're relying on seismic signals that are generated by meteoritic impacts or other sources. And so we're listening all the time. And this produces a pretty good torrent of data. For an actual event, we intend to collect data sampled Nyquist up to 200 hertz, so 100 hertz at 24 bits. And for long duration listening, where we're buffering at the higher rate, we'll listen at 10 hertz and 16 bits. We do have some thermal requirements which can be addressed through thermal design and management, which are related to the laser operation. We use a VCSEL laser that stops lasing at around minus 45 Celsius. And I mentioned before, there are no leveling requirements. So let me just motivate the rationale for burial. And some of you may be familiar with this. The lunar regolith is very fine powder that covers more than 90% of the moon, acts as a kind of an echo chamber. So you can see this is an actual Apollo signal. For the surface deployment, a P wave will come in. You can see there is some reverberation, which if there are returns that are coming from deep structures, are going to be masked even in the P wave. But then when the S wave, the shear wave, occurs, there's a very noisy reverberation that lasts for quite a while. Simulations of burial to show the benefit of burial indicate that by the time you get down to about a meter, most of the reverberation has been overcome. So, you know, if we could achieve burial even to 60 centimeters, we would be able to hear deep seismic signals probing the interior of the moon much more effectively than a surface deployment. But if we can get down to a meter, we've kind of reached the point of diminishing return. So that's our objective. In terms of launch opportunities, obviously we're looking at CLIPS. And for CLIPS, because of the duration of CLIPS and the requirement that it not survive a lunar night, although some of the landers do intend to survive a lunar night, we will propose a system without the burial system. And we've demonstrated in field experiments and also through finite element analysis that we can detect through the lander structure, given certain constraints on the resonant frequencies of the lander, seismic signals effectively. So I'm showing the Blue Moon lander here, which those of you who went to AGU and attended their briefing know that this is a pretty massive device. It accommodates, in the cartoon that they show, 3 Curiosity-size rovers, which are shown in this cartoon at the top of the lander. This is by far the most capable lander that I'm aware of for CLIPS. The others are much more modest, but given the accommodation requirements that I showed you earlier, we can fit in any of the selected CLIPS landers. The other possibility is the Lunar Geophysical Network, which is cited in the Planetary Decadal Survey. And I'm showing a concept from the 2017 study. Clive and Renee are in the process of leading a new concept study right now to better definitize the entire mission and get to the point where it could be considered for selection. So that brings me to the end, if there are any questions.
Hey, Hop, we're kind of a little over on time, so I don't think we're going to be able to take any questions. But if you look at the group chat, you can see the questions from a few people, and maybe you can respond to them directly in the group chat. That would be great.
I'd be glad to do that.
Thank you.